Today's topic we're going to study is electrostatic potential. For a change now, let's watch a video first.
Hello. Welcome to another physics video. Our topic today is electric potential. There are certain configurations of electric charge that create interesting electric fields. We will explore one such situation. Suppose we have two large, flat metal plates. We will make one plate have a positive charge and the other will be negative. It might look something like this. Suppose the plates are close enough together that they look very large to us. They are separated by a distance we'll call d. The top plate has a positive charge and the bottom one is negative. What kind of electric field do you think will be created by this arrangement of charges?
I know that electric fields will point away from positive charges and towards negative charges. So, I think there will be a field that somehow points downward.
That's a good start. But, before we can draw what it looks like, we need to think about what the field for two positive charges next to each other might look like. Suppose we zoom in on three positive charges in the middle of the long line of positive charges on the top plate. We know that the electric field will go away from each charge and we know the lines will appear to repel each other.
Once we get a little bit away from the charges, the lines look like they are parallel.
That is an excellent observation. Don't forget that there is a line of negative charges beneath these that will be attracting these electric field lines. If we now zoom back out and look at the entire line of charges, here is what the field will look like. Notice that the lines are parallel to each other and travel from the positive plate to the negative plate. Now, what do you remember about the spacing between the lines?
If the lines are far apart, the field is weak, and, if the lines are close together, the field is stronger. Does that mean that if the spacing between all of the lines is the same, that the field is the same everywhere?
That is correct. If the spacing is constant, the field is constant. We call this a uniform electric field. Notice how this is very similar to the situation with gravity if we are near the surface of the Earth. If the Earth looks large and flat to us, then we say that the G field is uniform. That means that G equals negative 9.8 everywhere near the surface of the Earth. Now let's suppose that we have a single positive charge lying near the negative plate and we want to lift it and move it so it is near the positive plate. The uniform electric field will exert a constant downward force on the positive charge. We want to lift the charge so that it remains in equilibrium.
So we have to match the force exerted by the electric field.
Yes. When we have moved the positive charge all the way to the positive plate and it is at rest, it will have gained potential energy. The electric field applies a force equal to the product of our moving charge and the field strength. To maintain equilibrium for our moving charge, we need to balance the force from the electric field. How can we calculate the work done by our constant force?
Work is the force times the distance the charge is moved.
Excellent. So, if we substitute the force we must apply, the charge Q times the field strength, we get the work is equal to the charge Q times the field strength times the distance.
The result of doing work is to change the energy of the charge. Since it is at rest, the energy gained has to be potential energy.
We know the change in potential energy for our specific charge. We would like to have a quantity that describes how the plates will affect energy. We will call this new quantity electric potential difference because it tells us about changes in potential energy in an electric field. The electric potential difference, also called the voltage difference, is defined as the change in potential energy divided by the charge that was moved. Putting everything together, we get electric potential difference is equal to electric field strength times the distance between the plates. A storm cloud builds up negative charge on the bottom of the cloud.
Then the electrons on the cloud repel electrons in the ground, pushing them deeper into the ground, leaving a positive surface.
An electric field is created between the cloud and the ground and a difference in electric potential exists between the ground and the cloud.
This is a real-life example of the parallel metal plates. We can use the same equations to determine how strong the field is.
See you later.
Hope you saw the video. Now you got the basics of what's potential. Now let's start with the topic. So what we're doing today is chapter electrostatic potential. For this, what we want to know now is these. Let's go back to the chapter 1, what we did. There are some information we should know. The first thing is we did about Coulomb's law, which is F force equals to 1 upon 4 pi epsilon naught Q1 Q2 by R square. And we also did electrical field, which is 1 upon 4 pi epsilon naught Q by R square. Here in both the conditions now, we never use a sign of charge. We always use a mod here. So we never use sign, it's always only Q1, Q2. Even if it's plus or minus, we always used plus only. And also, electrical field is force acting on a charge is electrical field. So I can say F is always equal to Q into E. So if you take this as a test charge now, you can say Q naught E. So this is a force acting on a charge when placed in a field in front of a charge. So these are things we did, and apart from that, we did your Gauss theorem and all these things. So what we want to know, why we are concerned about this now is electrostatic potential is the most important part of your physics before studying current. So what we do is, let's consider a charge. Let's consider a charge. Let's consider a charge Q. It's got its own magnitude. And it's got its own electrical field, which has been seen everywhere. You can see the electrical field lines are going everywhere now for this. Now in this line field, we're going to have 2 points now. Let's take point A and point B. Imagine if you keep a charge somewhere around here and let this charge be a very small charge, let's say a test charge. So you should know one thing now, this should be a small charge because this charge will repel this charge with a force in this direction, because both are plus now, so you can expect this charge to push this in this direction with the force F equals to Q naught E outwards. So this should not try to push it this way. That means this should not have its own magnitude and field on its own. It's a very small charge. So this charge has got a very small value. So this is a unit proper charge. So they will try to push it this way. So what happens now when you keep a charge, and on that field, if you keep another test charge around it, anywhere, the sure problem we're going to face is this plus will try to push it in the opposite direction. If I want to push this charge in this direction, this way, my biggest worry is this charge, this force is always pushing me in this direction. So if I want to push in the opposite direction now, I have to overcome this force by giving equal opposite force to just start moving in the opposite direction. So I have to do a mechanical work to push this inside on the opposite direction this way. And this mechanical work done by me is stored as potential energy on this charge. So what is the reason when you move this way is this repulsion is going to be much more and more. The problem you're going to face now is when you're here, the repulsion force is different. When you're here, the repulsion force of this is very much more. So this force which you're going to give now is changing as you come in now. It's a variable force acting. So let's now understand one thing now. So if you want to move a charge, the mechanical work done by you is going to be stored as energy. So imagine a charge Q, and let's have charge A and charge B. There are two information we should be very clear about. One is potential and other one is potential difference. So these are two information we should know first of all about, then we think of understanding the other things properly. So what is potential first? Let's go for this first. Let's find out now. Imagine I move a charge from infinity. Infinity is from the distance from here, it's infinity. So I'm moving a charge from infinity and I'm going to push the charge in this direction. So as I told you, as you push in, I'm just taking a test charge anyway. This test charge will be repelled in the opposite direction. So when you try to push in the opposite direction now, they'll try to be pushed that way. You have to go this way. So I'll do some work to move my charge from infinity. So let's say I'm going to move the charge from infinity to point A. I'll be doing a work to move a charge from here to here. And that work done by me to move a charge from infinity to this point A is always considered as potential at A. Potential is denoted by V. V is a potential difference anyway. So when the work done to move a charge from infinity to point A is always called as potential at A. Similarly, the work done to move a charge from infinity to point B will be called as potential at B. So it's very natural and clear that we'll not do the same work to move from here to this and this to this. So my potential at A and potential at B are going to be different. So first understand this concept now. Potential at any point is always defined as work done to move a charge from infinity to that point. That means if I move from infinity to A, it's called potential at A. When I move from infinity to B, it's called potential at B. So potential A is different, potential B is different. These two are two different values now, and if I subtract these two values, it's called my potential difference. So understand that one information, that potential is for a point and potential difference is a potential between 2 points. So this is the first information. So the next thing you should know is, so potential is work done to move a charge from infinity to that point. If a question is asked, let's imagine now there's a plus charge, there's A and there's B. Now which has got more potential? So there's a potential at A, there's a potential at B, we know that. Which is more? Let's have another diagram with minus charge A and B. So if the question is asked which has got more potential, what we should know is when you're near a plus charge, if there's a plus charge now, near plus charge, the potential is always more, and near minus charge, the potential is always less. So potential at A is more than B because A is closer to plus charge. Potential B is more than A because B is away from minus charge. So A is closer, or in other terms you can say potential A is less than potential B because it's close to minus charge. So when you're close to minus charge, you're at low potential zone. When you're near the plus charge, you're at high potential zone. So clearly VA minus VB here is positive and VA minus VB here is negative. So near plus charge is always high potential. That's another information you should know. So potential is work done to move a charge from infinity to some point. So let's find out an expression for potential difference. So this is expression for potential difference. Potential difference is PD. Potential difference I'm taking now. So how to do? So let's take a plus charge and consider 2 points A and B. Let the distance A be at distance RA and B be at distance RB. I have to find the potential difference between those 2 points. So work done to move between these 2 points. So what I'll do, I'll consider 2 points P and Q close to each other, and the arrow mark this way is going to be the DL. So DL is the vector in the left direction. So I can make out that DL gets bigger and bigger when I move towards left, towards the plus charge. So now what we'll do, we'll keep a small test charge Q0 at this condition. So what happens instantly when you place this plus charge, you try to push it this in the opposite direction, so it will be pushing it this way. So there will be a repulsion force in this direction. Next, because it's going that way, I have to move in this direction now. I have to give an opposite force in this way, which will be minus Q0E, the minimum force required to push towards P to Q. So my force I need to give is minus Q0E, and the distance going to move is dl. So the electrical field from plus, so plus has got electrical field in this direction because plus electrical field always go out. So the plus electrical field is this way, and I'm moving in this direction, dl. So between E and dl, the angle is 180 degrees. So that's also clear now. We have an angle of 180 degrees now. We're going against the field. So 180 is this thing. So let's find out work done. That's the whole idea now. Work done is going to be F dot dl. We know work done is force dot dl, and FDL cos theta is the formula. So FDL cos theta will be the work done to move from P to Q. If I want to integrate and find out work done to move from B, then it's going to be RB to RA. So I'm going to find out the work done to move a charge from B to A. That's what the idea is. And force here is, I'm giving a force of minus Q0. So it's going to be minus Q0 E dl cos 180. Why I'm taking 180? Because angle between E and dl is 180. This is RB and RA. So understand this now. There's a plus charge here. There are 2 points taken, P and Q, and A and B are 2 points anyway. My idea is to find work done to move from B to A. So I kept a small charge at point P. So the repulsion force is outwards. So I had to push in the opposite direction. So I give a minus Q naught E to push it this way. So the force I'm giving is minus Q naught E. Distance moved is dl. So I've got force dot distance dl is your work done, and F is Q naught E dl, and I'm putting a minus now. And 180 is because electrical field, and this is 180. So let's continue this. Cos 180 is minus 1, we know that. So this becomes minus integration RB RA. It's minus Q naught E dl, and cos 180 is minus 1. So cos 180 is minus 1, so minus 1. So minus minus become plus now. So we get something like plus Q naught E dl integral RB to RA. So I'm going from B to A, so RB RA. Now what I'm going to do is I'm going to take out dl and put dr. So dl will be minus dr because they are in opposite direction. Because dl is in this way, increasing that way. Dr is increasing that way. So dl for dr minus कर सकते हैं. So it's going to be Q naught E minus dr integral RB to RA. So this is the point now. Then we know electrical field due to a point charge. So electrical field due to a point charge is always given as 1 upon 4 pi epsilon naught Q by R square. So Q naught I know, dr is okay, small distance. So Q ka E ka value you have to find out. So let's put the formula for electrical field. So what I get is going to be integral RB to RA. Q naught is Q naught, right? Q naught. Electrical field the formula is 1 upon 4 pi epsilon naught Q by R square minus dr. So this is what we get. So minus, take it out, and you also know integration that dr says your r has to be integrated. So anything other than r is a constant. So keep r square inside, everything you take it outside, including the minus sign. So it's going to be, so first write minus, I've got Q naught, Q 4 pi epsilon naught, integral of 1 upon r square dr, RB to RA. So we have to find the formula now for that minus Q naught Q by 4 pi epsilon naught. Let's take it that way. So integration, I can write this as r raised to minus 2 dr, RB to RA, was 1 upon r square to r raised to minus 2 dr. So if I use it this way, I get minus Q naught Q by 4 pi epsilon naught. So integration formula is going to be x raised to n plus 1 by n plus 1. So r raised to minus 2 becomes r raised to minus 2 plus 1 by minus 2 plus 1, RB to RA. These are the 2 points. So it's going to be now minus Q naught Q by 4 pi epsilon naught. This becomes r raised to minus 1 by minus 1 RB to RA. So this minus and this minus is cancelled. So I've got Q naught Q by 4 pi epsilon naught, and r raised to minus 1 will be 1 upon r RB to RA. So this is what I get now for your work done. So all of things are work done now. So the work done equals this much. So I've got work done on the left side. Q naught Q, let's take it that way. 4 pi epsilon naught, constant there, keep it. Now you put upper limit minus lower limit. So upper limit is RA and lower limit is RB. So take this Q naught down. So work done upon charge Q naught is going to be equal to Q by 4 pi epsilon naught. Open the brackets now. Q by 4 pi epsilon naught RA minus Q by 4 pi epsilon naught RB. Now let's stop here. Let's finish off here, as we'll just stop off now. Now this is potential at different positions now. If this question has been asked in such a way that the question was, what will be your potential at A? I found potential difference between A and B now. If the question would have been A, then we already said that potential at any point is always work done to move a charge from infinity to that point. So if I want A alone, then my limits would have changed. Instead of RB, it would have been infinity. So what happened is the same derivation I can continue, and instead of RB, I'll put infinity now. So when I move from infinity to this thing, it's my potential at A. So I want A now. So what I'll do, this I took infinity, this I take infinity now. This becomes infinity. This becomes infinity. So this becomes infinity. You know 1 by infinity is 0. So this part will go. So this is the formula for potential at A. So you should understand one thing now. This is potential at A. and this is potential at B, because when I make it RB now, I'll get this and this will be infinity. So clearly, work done upon charge is going to be equal to, this is potential at A and this is potential at B. So this is A and B, I got this, instead of B I put infinity, I'll get this only. So this is the potential at A, this is potential at B. So work done upon charge is always going to be defined as potential difference between 2 points A and B. So this is the expression for potential difference between 2 points. So if they ask you for potential difference between 2 points, take A and B and derive. If they ask you for potential at A only, instead of B you put infinity, then this will go, you get this only. So same derivation, change the limits, you got the answer. So that's the first thing now for potential difference or potential anything, you can do it in one shot. Just change the limits now. If your limits is B, RB and RA, you're getting finding out for B and A. If it's infinity and RA, then you're finding out for V only, A only. That's a condition. The most important information other than potential difference is work done to move a charge in electrical field is conservative. So this is another very important information you should know, that work done is conservative. That means work done to move a charge, for example, let's take a plus charge now and let the electrical field be everywhere. So imagine I'm going to move a charge from A to B, from A to B in this direction, from here to here. I'll do some work. So my work done is going to be A, B. It depends on A and B. So this is RA and this is RB. Even, for example, I moved in this direction. Instead of this, if I go in this direction and take a turn and come to B, even in that case, my work done depends on RA and RB only. That means my work done to move a charge from A to B around a charge depends only on the starting point and ending point, not on the path followed. So I'm not worried about which path I'm following now. I'm only worried about where I start and where I end. That's the reason why this conservative concept is proved here in this equation. Work done upon charge equals to 1 upon Q naught, Q by 4 pi epsilon naught, 1 upon RA minus 1 upon RB. This derivation clearly proves one thing now. This work done upon charge depends on, this is constant. This constant, it depends on RA and RB only, because these two are constant already. So work done depends only on RA, the initial point, RB, final point, and not on the path followed. So if there's a question asked in the paper that derive expression to show work done is conservative, once again do the same derivation of potential difference and finally write that the work done depends on RA, RB and does not depend on any other thing, so it's conservative. So you should know the question is different but the answer is same. So same potential difference, we can find three things now. We can find potential difference, we can find potential at any point, also we can prove conservative, that is work done depends on initial final points, not on the path followed. So this is the first important thing. So now we are getting this formula now. Work done potential is going to be 1 upon 4 pi epsilon naught Q by R. This is what we did, we just got just now. The big difference between the formulas we did for force. Force is 1 upon 4 pi epsilon naught Q1 Q2 by R square, Coulomb's law. And electrical field, which is 1 upon 4 pi epsilon naught Q by R. So these two formulas and this formula has got a very, very important difference, and important difference there is these two are vector quantities and this is a scalar quantity. It's work done now, it's a scalar quantity basically. So in these two formulas now, we never use the sign of charge, it's always mod. Even as plus, even as minus, it's plus only. We never take minus charge. But here, in case of potential, if it's a minus charge, you have to use a sign. So sign should be used in case of potential, which we are not done in the before chapter. So wherever there's a minus sign, it should be used. So potential may we'll use sign now. So I'll tell you how to go about it. So we have to remember that sign has to be considered in potential because it's a scalar quantity. For example, I have a charge plus charge and I've got point A at distance R. If I ask you what's potential at A, then my formula will be V equals to 1 upon 4 pi epsilon naught Q by R. That's a potential at A because of this charge. If this charge would have been a minus charge, if I ask you what's potential at A, then I'll write this, but I will take the minus sign as well. That's what I'm trying to tell you now. Sign has to be considered when you're using potential formula. So if there's a minus now, use minus. If it's a plus now, use plus. So sign has to be considered. It's a big major difference between the ones we did before and after, number one. Number two, I'll give an example now. Let's take a charge. Let it be 5 coulomb minus 2, 5, let's take plus 3, and let's take minus 5 and plus 2. If the question would have been, let's take, this is all 1 meter, 1 meter. So this is your hypotenuse, it will be root 2, because Pythagoras theorem 1 upon root of 1 square 1 square. So if I ask you what is electrical field at point A, at point O, electrical field at this point center. So electrical field you can easily find out, because electrical field we keep a test charge and see how it moves. This 5 coulomb will repel the plus charge in this direction. So clearly the 5 coulomb electrical field will be outwards. Minus will attract this plus charge, so they will also be pulling the plus charge this way only. So both the electrical fields will add up to become E1 plus E2. Similarly, this plus 2 will repel this plus charge in this direction, so it will be E3. Minus 2 will attract plus, so same direction will move, so E4. So my electrical field, because of these two are adding up here, so I got electrical field this value, I got electrical field this value, and my resultant is going to be my net answer now. So if my electrical field, if I ask you, then you find out E1, E2 using the formula of electrical field, then E3, E4, add them up, and net formula you use vector addition under root of E1 E dash square plus E double dash square. Then E dash is E1 plus E2 and E double dash is E3 plus E4. So this is the thing we do for electrical field, which we did nicely in the first chapter. If the same question has been asked for potential, imagine I got the same diagram, 5 minus 3, I got 2 I think, plus 5 minus 5 plus 2. What's potential at point O? If they ask you, we cannot do the concept of arrow marks here, because I can't do the same thing what I did there, outwards, inwards, nothing is possible. Potential, the distance from this charge, this center is R, this is also the same distance, from here to here also same distance, here they are same distance, center, so all at same distance. Now you should understand one thing now, the distance from each charge is same at center. If I ask you what's potential at A, it's potential due to this charge plus potential due to this charge plus potential due to this charge plus potential due to this charge. My potential formula is going to be 1 upon 4 pi epsilon naught Q by R. That's a formula now anyway. So I'll do 1 upon 4 pi epsilon naught Q by R for everything. So 1 upon 4 pi epsilon naught Q is this by this R. 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 So if I'm going to do all the formulas now, so I can get one information clear now, 1 upon 4 pi epsilon naught is common. I can take it out. Even R is common, let's not take the R, let's take R separately. Q by R. So Q for the first case is 5, so 5 by R. This is minus 2. As I told you, take the sign, minus 2 by R. This is minus 5 by R plus 2 by R. So K 1 upon 4 pi naught Q by R, so common. So 5 and minus 5 cancel, 2 and minus 2 cancel, the answer is 0. So the same charges, same question, but in one case we did not take the sign, we just took the vector addition, we got some answer there, electrical field was there. But in case of your potential, we've got answer 0. Even if I'm going to change my charges ka position, for example, if this minus has been taken here and minus plus 2 here, then also my answer will be 0 only. So potential, finding out calculating potential now, we are not worried about where the charges are placed. If I shift my charges to different positions now, still I'll get the same answer. But electrical field is not so. Electrical field answer will be different, because now this is plus, keep a test charge here. Now this plus will repel it this way, and this will try to repel it this way. So the electrical field is now getting subtracted now. They're not cancelling out, subtracted. Minus 5 will attract this way, and minus will attract this way. They're getting subtracted. So you're going to get a different answer here from back to what we got before. So electrical field at any point depends on charge distribution. It depends on where the charges are placed. You change the position of charges now, automatically the answer will be different. But potential, may you do anything with the charge, nothing is what happen now. Charge can be anywhere. We are bothered about the net, total net charge which is present now. So if I'm going to, if this kind of question comes now, if R is same, So I know one thing, V equals to 1 upon 4 pi epsilon naught Q by R. As I told you now, Q by R, you can do it in a very short method now. These two are same. A भी same है question में. So these two are common anyway. So you have to only take the net charge. If your net charge becomes 0, that means your potential is 0. So just add all the charges now, and if the answer is 0, 0. But that implies only when your R is same. Be careful now, the distance of all the charges should remain same. So automatically, if this R is equal now, you can commonly just add all the charges now, answer 0, 0 answer. So in 1 second, you can get the answer, provided it's at same distance and condition is same distance hona chahiye. That's the most important thing. We just did now that potential due to a charge is 1 upon 4 pi epsilon naught Q by R. And also, if it's minus Q by R. Now what we do, we'll now have two charges. Instead of one charge now, we'll have two charges. So I'll have a minus Q and a plus Q. So let's find out, let's have minus Q plus Q anyway. So let's now, this is a minus Q and this is plus Q, means I'm talking about a dipole. So let's take a dipole and let's have two charges at distance 2a. So we know dipole is distance at same distance, 2a is your dipole. So it's going to be the case now. And I'm going to find out electrical field at any point, potential at point P, because of this from a distance r from the center of charge. So this is my I'm going to find potential here because of two charges. So it's exactly like what you read in the electrical field. And we also know when there are two charges of same magnitude placed at 2a, it's called dipole. And this line which is joining them is called an axial line. So what I'm going to do now is we'll find a formula for potential on axial line of a dipole. So that's the idea now. So this will be R minus A and this will be R plus A. So that's a whole idea now. So my potential at P will be potential due to this and this. So it's going to be 1 upon 4 pi epsilon naught minus Q by R plus A plus 1 upon 4 pi epsilon naught Q by R minus A. So I can take this way, that way. So you can take any way you want. So let's take this minus also, even this plus also. The answer is going to be same. The only thing is this is going to be plus here. This is going to be a minus sign. So it's any way you can do it. So you can take this way or that way. It's okay. So push anyway. So now if you take Q common by 4 pi epsilon naught, it's going to be Q by R plus 1 by R plus A minus 1 by R minus A is what we get. Because so now I'll take LCM now, take common. So when you take it common, it's going to be Q by 4 pi epsilon naught. Take it this way, this is R square minus A square. And LCM you take, it's R minus A, R plus A. So it's going to be Q by 4 pi epsilon naught. This is R cancel. I've got minus 2a here. R square minus A square. So Q into 2a is dipole P by 4 pi epsilon naught R square minus A square. I've got a minus sign, so potential comes in negative here. So if you have taken plus and minus other way around, you'll get a plus there. So it's not an issue of that. So it's minus or plus. So here it's minus and minus, so it's minus now, since I've taken a plus this way and minus that way. So end of the day, the magnitude is going to be, this is a formula for potential at an axial line of a dipole. So Q into 2a is P, so Q into 2a is P by 4 pi epsilon naught R square minus A square. That's going to be the formula now. So if you take for equatorial line of dipole, so if this is going to be a plus and minus, this is A, this is A, this is R, this is under root of R square plus A square, this is also under root of R square plus A square. So if I ask you what's potential at point P, it's going to be potential due to this and this. So from here to here, same distance, from here to here, same distance, same charge. My potential will be for this plus charge will be 1 upon 4 pi epsilon naught q by r, q by this r, which is under root of r square plus a square plus a minus s. So minus q by 4 pi epsilon naught root of r square plus a square. So q by r, q by r. So plus and minus, same answer. So these two gets cancelled to become 0. So potential difference or potential at any point of axial line, the equatorial line of a dipole, is always going to be 0. So you should know this very importantly. We have a formula for electrical field on the equatorial line of dipole, which was P by 4 pi epsilon naught r cube for a short dipole, or r square plus a square raised to 3 by 2. But in case of potential, the equatorial line, your potential is going to be 0. So there is no potential difference across the line which is going to be on the equatorial line of dipole. So on the complete line, on this line completely, the potential is going to be 0 for this thing. So it's a very straightforward and a small derivation you have. But there's one extra information in this chapter, which is potential at any point due to dipole. So it's there's a extra information. This is got at any point due to dipole. So let's do that. Point due to dipole. So the diagram is very important. Let's understand the diagram first. Let's take a minus q plus q dipole I'm taking from center. This line is equatorial line, this line is axial line. So I'm not taking axial line, equatorial line. I'm taking any other point somewhere, not an axial line, not an equatorial line, but at some distance r from at an angle theta with the axial line. So I'm going to find a point P which is not in axial line, not in equatorial line, somewhere on the point which is not lining these 2 points now, so it's angle theta. So this is angle made between this and axial line theta. So with axial line, when I take my point at P here, my theta will be 0. When I take my point here, my theta will be 90. So axial line ke theta 0, equatorial line ke theta 90 ho jayega. So that's a condition now. So I want to find out potential at this point due to the dipole because of this and this. Let's now name it as A and B. Now, what we do is, this is A anyway. So let's take this as A. Let's take this as A. So let's understand the diagram first. Now, like this, let's make this line straight and make a right angle triangle like this. Let's name it as M. Now, this is theta, this will be theta. Now, let's take this center as, say, O. So, AOM is a right angle triangle. So, triangle AOM, right angle triangle, if you take, cos theta will be equal to OM by OA, which is OM upon A. So OM can be written as A cos theta. That means this distance will be A cos theta. So from here to here is R. From here to here is A cos theta. For the complete distance PM now will become R plus A cos theta. That's the first information we are doing it now. So I've just had a perpendicular drawn, I'm doing this now. So let's do the next thing, which is I take a perpendicular from here, drop it here. Let's take this as N. That means I've got another triangle BON, triangle BON. So the other triangle is going to be this triangle, right angle triangle BON. So let's take the right angle triangle BON as well. So triangle BON, cos theta for the triangle once again will be equal to ON by OB, which is ON upon A, or ON will be A cos theta. So ON also is going to be A cos theta. So this distance also is A cos theta now. This is A cos theta once again. So this distance is R and this was A cos theta. I added them up. But this distance is R and this is A cos theta. So R may one A cos theta is going off. So out of R, take out R, 1 A cos theta. So my Pn value will be R minus A cos theta. So this is what we have to understand from this diagram now. So the total distance from here to here is, this is R and from A cos theta, so R plus A cos theta. This is R and on that you take a cos theta out, so left-hand part is r minus a cos theta. So Pm is r plus a cos theta, r minus a cos theta. I'm considering only one thing here, which is just to make it easier, which is AP, that means this distance AP, I'm considering almost equal to PM. And A PB almost equal to PN. So instead of AP, I can write PM. Instead of PB, I can write this as PA. Instead of PB, I can write this as PN. So PA ki jagah pe I can write R plus A cos theta. In PB's place, I can write R minus A cos theta. That's the whole idea. So let's find potential at this point. Potential at this point is going to be potential due to this charge plus this charge. So potential formula is 1 upon 4 pi epsilon naught Q by R. So 1 upon 4 pi epsilon naught is common. Q dono ka same. Only R is changing. For this Q, the R will be AP, PA. For this, it will be PB. So let's put the potential, the formula here, and we get the answer. So potential at any point will be equal to 1 upon 4 pi epsilon naught Q by minus Q by PA, because PA ka charge is minus, plus Q by plus 1 upon 4 pi epsilon naught Q by PB. So take minus plus inside, so Q by 4 pi epsilon naught common. So this is minus, so it goes that side. So 1 by PB minus 1 by PA. So put the value of PA and PB. So instead of PA, I can write as PM, which is 1 plus R plus A cos theta, minus 1 by PB is R minus A cos theta, sorry, R minus A cos theta, and PA is R plus A cos theta, because PA is PM, so PA is this. So take Q by 4 pi epsilon naught. This is going to be R square minus A square cos square theta divided by, this comes up here, R plus A cos theta comes here, minus R minus A cos theta goes there. R get cancelled. You get A cos theta plus A cos theta is 2A cos theta. So what you get here is, I will get something like Q by 4 pi epsilon naught 2A cos theta upon R square minus A square cos square theta. But Q into 2A is called dipole moment P. We know that. So my formula for potential at any point due to dipole is going to be equal to P cos theta upon 4 pi epsilon naught R square minus A square cos square theta. So as I told you, when theta is 0, it's called axial line. So cos 0 is 1, so cos 0 1 is P by 4 pi epsilon naught R square minus A square. We've already done this formula now. This is axial line, this is for axial. So if you want to find theta is 90, that becomes equatorial. So when you put theta 90, cos 90 is 0, you get an answer 0. So we can check whether derivation is right or wrong. So it's right. So cos 90 is 0. So this is for axial, this is for equatorial. So you can find out axial equatorial separately, or you can do this and put theta 90. It's up to you. So this is the way to find. So you've got potential at axial, potential equatorial is 0. Any point is P cos theta upon this. So what we did just now is going to be, we did what is potential difference. We also did what is conservative energy, work done conservative when it depends on initial final points, not on the path followed. And also we did potential at any point due to dipole and axial equatorial line. Now let's go to the next part, which is when VA and VB are equal. So they are same potential now. When the potential is same on both the points now, then VA minus VB will be 0. Now this point where VA minus VB is 0, or when there is no potential difference, this is called an equipotential surface. So the first information, that is equipotential surface, if I use this word equipotential, that means potential at every point of the surface is same, or there is no potential difference at that point. So if I go back and check the example, we did this equipotential surface is where equatorial line of dipole. I told you equatorial line of dipole means there's no potential difference. So equatorial line of dipole, for example, if you have a dipole now, plus minus, if I ask you draw equipotential surface now, the first thing is equatorial line mein line draw karo. This is going to be an equipotential. But see to it that distance is same. At the bisector, that's going to be there. This is an equipotential surface. The equipotential surface for a plus and minus charge or a dipole is going to be the bisector, which is going to be there between them is the line. So this is going to be equipotential for your plus and minus charge because potential difference is not there. So first thing. Also, VA minus VB is work done upon charge. That's what we derived already. So when VA minus VB is 0, that implies work done upon charge is 0. That's right. When VA minus VB is 0, that implies work done upon charge is 0. That means work done to move a charge on an equipotential surface is always going to be 0. So you will not do any work in moving a charge on a surface which is equipotential. If I give you an example, once again I can take dipole plus minus, and if I go to move a charge along the equatorial line of dipole, so at distance A and A, if any charge is moved on this line, equatorial line of dipole, your work done will be 0. So there is no work done in moving a charge along the equatorial line of a dipole. That's a most important information. So work done is always 0 for equipotential surface. Other equipotential surfaces we'll see just now. So we know electrical field lines. We already know electrical field lines are always drawn from plus edge goes out, minus edge comes in. So this is something we are very sure at. Electrical field line for plus is outwards. And we also know this is how a test charge moves, plus test charge moves in a field. So this is minus. So this is something we know clearly. Now, how can you draw an equipotential surface? So we know electrical field line draw karna kaisa hai. How can you draw an equipotential surface for a charge which is solitary, one charge? So how can you draw equipotential now? How can you do that? Let's find out. So for that, let's find out what's an angle between the electrical field line and equatorial line of dipole ke beech mein. What's the angle now? That's what is very important now. So we know work done upon charge is potential. So potential difference. Work done upon charge is also equal to F dot dl upon charge. F by Q is E. So work done upon charge can also be written as E dot dl. So work done upon charge can be potential difference also. Work done upon charge can be E dot dl as well. So when VA minus VB is 0, that implies my E dot dl will also be 0 because they are equal. So this implies E dl cos theta is 0. E cannot be 0. dl cannot be 0. So your cos theta should be 0 or theta should be 90. So what we are trying to prove here is the angle between equatorial line, angle between the equipotential surface and electrical field lines are always going to be at 90 degrees only. So electrical field lines, if you know, you can always draw equipotential surface. So draw a line in such a way that the electrical field lines and equipotential ke beech mein the angle should be 90. So you should draw lines in such a way that electrical field lines should be cut at an angle 90, and that line you're drawing which is cutting at 90 to electrical field line is your equipotential surface now. So equipotential should be exactly cutting your electrical field lines at 90. So the simplest example we can say is an uniform electrical field. Uniform electrical field is always this. This is a uniform electric field this way. So uniform electrical field, if I want to know what's equipotential surface now, you should draw a line which is bisector 90 degrees now. So the best line is 90, this one. So this is an equipotential for a uniform field. This is one equipotential now, maybe at some point. I can draw one more here somewhere. If you want to draw it. If I want to draw some more, I can draw one more. So this has got its own potential, this point. This point will have its own potential. This point have its own potential. But on this line, the potential will remain V1 only. So all these lines will be V1, V1. All these lines will be V2, 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 and all these lines will be V3, V3, V3. So these are different equipotentials now, but this line has got same potential on same path. So if you want to move a charge in this direction, that means along this line, then your work done will be 0. So work done by moving a charge in equipotential surface is 0. An example equipotential is this one. So electrical field line ka 90, the line drawn is equipotential. So if you move a charge along equipotential line, it's going to be 0. So work done is not there for this condition. So if I want to know draw an equipotential for a plus charge, then it's going to be I will draw lines cutting all this at 90. So the best thing is circle. So this is an equipotential for a charge. So if you have a spherical surface, the surface of a spherical sphere is always equipotential. Surface of sphere has got same potential at every point from center. So potential at every point for the surface which is spherical is going to be same, or the work done to move a charge on a surface of a sphere will be zero, because there is no potential difference here, so there is no chance of any potential being used there. So work done to move a charge on the surface of a spherical surface which is equipotential will be zero. That's the main information now. So equipotential can be easily drawn. So if you have electrical field line, cut them at 90 degrees. So that's going to be equipotential now. So let's have an example. Let's find out whether we understood things or not. Let's have 3 points now, A, B, and C. Now, between A and C, which has got more potential is a question. So A has got more potential than B, or A has got more potential C, or C has got more potential A. What is that? So let's find out now. So if your question is given to you like this, more potential. I told you already, potential near plus charge is always more. So where is the plus charge here is something we should know. So electrical field line is this. We all know electrical field line always go from plus to minus. So my plus should be here anyway. So this is my plus charge. And when I see the distance from the plus charge to A and plus charge to C and B, clearly my A is closer to your plus charge. So potential at A will be more than C and B. Interestingly, C and B are a 90-degree line drawn to this thing. So this is an equipotential surface. So B and C will have same potential. So potential at B will be equal to potential C, because I've drawn a 90-degree line to the electrical field line, which is equipotential. So they've got same potential from B to C. So A has got more potential, B has got same potential. If I'm going to move a charge from B to C or C to A, my work done will be C to B, my work done will be zero. That's the first information, that work done to move a charge and equipotential is zero here. But if I'm going to move a charge from say C to B to A, what will be my work done? What will be my work done? So work done to move from C to B to A will be equal to moving from C to A only, because I told you in case of electrical field, your work done depends on initial final points, not on the path followed. I am not worried about where you go and come. My starting point is C and my ending point is B. So my work done will be between C and B. So clearly here work done will be between C and B. That's a work done for me, which is work done is force and distance. That's okay. Now, so clearly this is an example of conservative information now. That means C to B to A. I'm not bothered about B. C and A is what we need. So C ka portion we know, E ka portion we know. We can find work done. We can find potential difference, which we can do it easily. So this is the information to apply or find out which has got more potential, which has got this thing and all this stuff. So let's give another question now. Example: I have A means there's a charge, and I've got equipotential surfaces now. So I can make out A is a single charge. Single charge equipotential surface will always be circle anyway. I've given the values of this. Each and everything has got a potential. This one equipotential surface, it's got another potential. So everything has got a value. So let's give the value for this now: 10 volt, 20 volt, 30 volt, 40 volt. So the voltage is, I can see, increasing outwards. The question is, what's a charge at A? And draw the electrical field line for that. So I should know what the charge there is. Is it a plus charge or a minus charge? And I should draw the electrical lines for that. How do I know that? So it's very simple. I am moving inwards towards it. I can see the potential starts going down. So my potential was 40, then it's become 30, then 20. Potential is going down. I told you already, towards a negative charge only your potential decreases. So clearly this decrease of potential clearly tells me that the charge at center is going to be a negative one. If my answer would have been increasing now, for example, this is 10, this is 20, 30, 40, it would have been plus now. So since it's going down, the voltage is going down, it's a negative charge, my electrical field lines are going to be like this. So this is the example of how to use your logic of equipotential and also the potential zones which has got more potential and less potential. So this is the information now. So this is a small information you should know to do it. So we also know that work done upon charge is potential difference. So this is going to be the condition. So work done will be charge into Q naught into potential difference. So let's do that. So work done is minus Q naught E dr, which is force and distance. I already used this derivation formula in the before derivation. So Q naught is force, distance is Q naught into VA minus VB. So this is force, this is distance. Okay, Q naught get cut. So minus E dr will be, this is VA minus VB is dV only. So E will be equal to minus dV by dr. So this is a very, very important relation between potential and electrical field. So E is always equal to minus dV by dr. V is potential difference and R is your distance. So basically electrical field is minus dV by dr is a formula for electrical field relation between E and V. So E is electrical field, V is potential. To make this simpler, the easiest way to remember this, I'll tell you what's the easiest way to do it is 1 upon 4 pi epsilon naught Q by R square is my electrical field formula. My potential formula is 1 upon 4 pi epsilon naught Q by R. So when I divide these two equations now, clearly divide करो दोनों के equation को cut एक R बचा है बस. So E is going to be V by R. So this is the simplest logic to say E and V का relation is E is V by R. So electrical field can be written as V by R, V by D, V by L. So my R can be given in terms of L, D, X, कुछ भी करो, it's okay. But your E is V by R or V by distance is your. So this is called your dV by dr or V by R is called your potential gradient. So gradient is always something which changes the distance now. So the interesting information we're getting here is E is minus V by R. So minus dV by dr is what we got now. This is what we get. So since E is dV by dr in terms of mod potential, even take minus now. If E is 0, that means there's no electrical field, then my dV by dr becomes 0 or differentiation of a constant is 0, so V will be constant. So when electrical field is 0, that means voltage is not 0. When electrical field is 0, that means your potential is going to be same or constant. So the example of this is when there is no electrical field in a region, in that region potential will not change. The biggest example is your spherical surface. So potential, if you have a charge on a surface, on a spherical surface now, if you have a charge, the potential of this charge at surface is 5 volt. Then from here to center, the potential will remain at 5. So at center also the voltage is 5 volt only. So any spherical surface with a charge has potential of 5 volt. Then electrical field inside a conductor is 0. So clearly inside a conductor electrical field is not there. So potential is constant. So a sphere with potential 5 volt at center or at surface will have same 5 volt throughout this up to center. So any point I consider, here I want what's the voltage now? 5 volt only, 5 volt only. So inside a sphere, the voltage will remain constant. The surface and center of the surface is going to be center of the sphere and the surface of the sphere will have same potential because electrical field inside a conductor is 0. That's what is the information you should know. And the example to use E and R, sig V and R. Let's have a graph. If I ask you to redraw this graph in terms of E and R, so E is minus V by R. That's what I told you already. That means your V by R is the slope of the graph. Minus V by R is negative slope of the graph. So this graph indicates one thing now. Minus V by R, the negative slope of this graph gives you positive V. This is my negative slope of V by R. This is going to give me positive V. And positive slope of this graph is going to be give me negative V. And here there is no change in voltage. So this line will not have any change. So V is constant. So dV by dr. So there's no change in voltage. So clearly my electrical field will be 0. So if there is no change in voltage because E is dV by dr, when V is not changing, that E will be 0. So V is not changing in this line. So if I name it as A to B, between A and B, there's no change in V. So since V is not changing, so V is constant, so E should be 0. So A, B may voltage electrical field is not there, but here electrical field is negative because it's a positive slope. Here electrical field is positive because negative slope. So clearly my diagram will be electrical field is negative because it's positive slope minus E. It's 0, this is negative, it's positive slope. So this is plus C. So clearly, if you have any graph given, understand one thing now, if my V by R is positive, my electrical field is negative. When V by R is a straight line, radical field is 0. And V by R is this way, horizontal line is 0, then it's going to be negative slope, it's going to be positive E, is the information you should understand. So this potential part of chapter has got these informations now. There is potential difference, potential due to dipole, and potential at any point due to dipole, equipotential surface, and of course your usage of equipotential surface now. The very important last information I would like to tell you is E is dV by dr. E and R basically, for example, if I have an equipotential surface where potential is, I have a uniform electrical field. If I want to draw 3 equipotentials for this, 3 equipotentials, when you draw, be careful now, the 3 equipotentials should be drawn in such a way that the gap between the equipotentials should remain same. So the gap between equipotentials always depends upon the radical field. So if radical field is stronger, then the gap between equipotential gets closer. When radical field is weaker, the gap between equipotential will be more. So here radical field is uniform, same uniform field, so my gap is going to remain same now. If my field is, for example, plus charge, radical field is decreasing outwards. You always know radical field decreases over, the gap gets big. If I want to draw 3 equipotentials line for this now, you cannot draw equipotential lines in equal gap. The gap between them should be decreasing, because if field decreases, the gap gets bigger. So the gap for the first one is going to be this. The first one का gap थोड़ा कम, next one का gap थोड़ा ज़्यादा होना चाहिए. So you should be very careful now. This gap of R1 and R2 should not be same for a non-uniform electric field. The gap between equipotentials will be depending on the radical field only. When radical field is stronger, then the gap between equipotential is closer. When radical field is weaker, then the gap between equipotential is going to be much bigger. So here radical field is constant, so the gap is same. Here radical field is decreasing now, you see the gap is getting bigger and bigger. So increasing field, the gap come closer. Decreasing field, the potentials will be away. So equipotentials are going to be spaced depending on radical field strength. If radical field strength is stronger, this is going to be closer, or away it's going to be weaker. So this is what we did in this chapter. First part is potential. So this has got a second part called capacitor. So we'll do that in the next video. Concluding today's session, let's check the summary. Until next time, bye-bye.